If I give you a velocity graph, it is the velocity. Then the derivative would be the acceleration, so the slope of the velocity is the acceleration. You know that. Alright, put that away, Sue.
Any observations from your reading last night?
It was from chemistry.
What'd you say?
The little chart thing.
Latent heat?
Yeah. I remember using
it should be kind of like chemistry.
Yeah, you should. In chemistry, she gave it to you the other way.
Really?
Yeah, she gave it to you as a non-function, which is kind of weird.
So we have
I don't remember.
We have two versions of our Q equation. We have one for temperature equalization where nothing is changing phase. And we have another one for that deals with changes of phase. So which one deals with non-phase changes? What does Q equal in that case? Heat. One of them was what we did yesterday.
C P equals Q.
Yeah.
Changing T.
Yeah, we just write it a little differently. The book has it with, what does the book set it equal to?
CP.
Specific heat?
Yeah.
Okay. Which is a constant. We like to do it this way, which is probably more like how you did it in chemistry. And what does it change its phase? We use something different. Because in phase change, what is not changing while the object is changing phase? This is the weird part. Say what? Mm-hmm.
Yeah.
ML, well what the heck? Shouldn't the temperature be changing if we're changing phase?
Oh, not
If
all
water
the time,
boils and turns into steam, it's because it gets hotter, right?
I thought
So-
it could be like it's the same temperature, but it's, I don't know, because like when you're saying how like the water bottle's in the freezer and it's still liquidized, and then when you move it, it freezes, and so it's still lower, but it didn't change any temperature, it just moved.
Right, good. Because when you're dealing with heat of fusion, which is a liquid to a solid, or heat of vaporization, liquid to gas, and we base everything off liquid because that's what water is for us. It really works both ways. But that heat involved there doesn't actually have the temperature. It's extra energy basically that the substance is going to use to rearrange itself to get into a new phase. So it's going to like use it to reconstruct itself in a different form.
That's weird.
So when you are going from a solid to a liquid, the ice needs to retain a bunch of heat without raising its temperature because it needs that heat just to become a liquid, for its molecules to do something different. So you kind of like rebuilding. Mr. Ernst is duplicating the chart on page 376.
Alright, so,
Question.
what is it?
For the D part, the part D, should the temperature increasing first and then decrease?
For B, increase and then
D.
decrease. Oh, I think this is just a break in the graph.
Okay.
It's supposed to be a straight line, but
So
really, water is a liquid for a long time. Okay, so that's why
Oh,
That's
I
there.
see.
it goes from 8 to 30, but we don't have room here on this scale where here's basically 1, 2, 3, 4, 5, 6, 7, 8. We don't have room, so we're just
So
slicing it off.
Do we use Q equals ML for B, and A and C on
Q equals ML for B, is that what you said? That's correct. There's somewhere else to use it too.
D.
D, yeah.
What is L again, AJ? I figured. What is L?
Kind of like how when I asked him for comments about what he read. Yeah.
Anybody, what's L?
What's L mean?
What is it? Latent heat. True or false, heat and temperature have a directly proportional relationship.
False.
False.
Yeah, false.
When you add heat to something,
When that,
when you add heat to something, the temperature increases, right?
we're just talking
No,
about
when
how.
You should have done this before you wrote the graph.
Phase change.
What?
When there is no phase change.
Yes, this is true conditionally. This is true assuming there's no phase change. The reason that this is false is because of this.
And
This
so-
is false, and the reason it's false is because it's not always true. Agreed?
Yeah.
Okay? The reason it's false is because of that. What is latent heat?
That was the heat used to change.
Yes, exactly. Couldn't have said it any better myself. Heat used to change phase.
I'm going to put energy used to change phase. I could have said it better myself.
Energy.
Thanks.
That's fine.
But you know I get why I say energy? Because this heat doesn't raise the temperature, and we always think of heat as raising the temperature.
Yeah.
And heat is a form of energy.
Energy used to change phase. So, like we talked about yesterday at the very end of class, water boils at what? But if you leave it on the stove longer, when it's at 100, you keep heating it up, it's going to stay at 100. It'll stay at 100 and evaporate.
Oh, okay.
Yeah,
You'll never have 110 degree boiling water.
at standard atmospheric pressure. Yeah.
Right, at standard atmospheric pressure. In Denver, does the water boil higher or lower?
It has lower.
Higher.
In what?
It has.
Denver, Colorado.
They're on a mountain.
Yeah, but they have less
Colorado,
pressure, so
1
they
mile
don't heat as
elevation.
much.
That's all. I just went higher.
1 mile up.
Oh.
So does the water
What?
boil higher or lower?
Lower.
It boils lower. Why?
Because there's less pressure on it.
Less pressure, so it's willing to change phase sooner.
Remember how I told you if we had a bowl of water in a vacuum, in like a sealed box, and we took all the air out, the water would boil at room temperature just because it wants to fill up all that.
That's why it's kind of interesting. You'll see some products that are manufactured or shipped to Denver, like on rice, it'll say add a cup of water, boil for
We talked about this when we were
X-
gone one day.
X
What
amount
happened
of
to
minutes, and then it says if in high altitude, if in Denver, and almost all things that are sold in Denver would have a high altitude direction, it'll adjust that and it'll say boil for 15 minutes instead of 10, because obviously the water boils at a lower temperature, so it takes longer to cook stuff. Interesting.
Yeah, but does it make any difference to cook for 30 minutes?
Yeah, because it's the heat. It's
Yeah.
the specific heat of water that's imparting heat to the. Well, if you're boiling noodles or rice.
Is it like a lot of different?
Yeah, it's about probably 3 or 4 minutes. I think it's about
Even more than that.
96 degrees, I think water boils at in Denver.
Celsius, I don't know. I think it's like 100 and. I
It
think
seems
it's like
a lot
190
more.
degrees
I mean,
Fahrenheit, so that might be about right.
Yeah, I think it's around 95, 96 degrees of water boils in Denver.
It's
It's a mile up, that's a lot.
Yeah.
You know, so
And that's why I said, when you said this water boil lower or higher, it boils higher.
Mr. Gottschalk was being literal. Because if you're in Denver, you're automatically higher. So water would boil higher.
The water's up there.
Because the water's up there.
You're gonna have to specify that on the test,
Or you can-
or everyone will get it right.
correct. Have you guys, Mick and Sue, seen that table before?
What kind? The graph, yes.
Yeah, yeah. Or graph, I should say, not table. What do the numbers on the bottom mean?
That's not degrees. It's not temperature.
And what is this?
And then,
It's heat.
This is a break.
oh,
So in actuality, this graph is about as long as the board, and D is far and away the largest section.
Yeah.
Okay. I didn't do it, sorry.
That's alright. Alright, go on. Heat's
And
on the bottom.
Yeah, the bottom. What are those numbers?
and
the amount of joules.
The amount of joules of D, okay. Thanks. I can read too.
It's
Why is it there? What?
Yeah, what?
What's the point of having heat on the bottom?
so like as the heat increases, there's
Well, here's the thing. This is probably a little. The table, I didn't quite finish it. We have -25, 0.
Well, you could add that fill it in.
This has to be obviously what?
100.
Why do you know it's 100, AJ?
Oh, because it's the boiling
It's more than
Of
water.
water. And then this is probably somewhere around what, 125? Somewhere in there, 125. No, it's not. It's 125.
it's 125.
50, no, it doesn't matter. I don't care about 50. 50 is just in the middle. Who cares? So, what this says is to get
C or 202.
to get water from -25 degrees C to 0.
Instantly 0.
What?
The
And this they should say specifically. This is for 10 grams. This is for a 10 grams, so 10 cc's. This is specifically, and that's what these numbers are relating to. 10 grams. A gram is the same as a cc. Gram is a what? Volume, mass. Gram is a mass. Cc is a volume, but they're equivalent to one another because they're standardized with pure, fresh water. Because we standardize the gram off of water. You guys remember that SI unit?
It was
Originally, it was standardized off of the cc of water, so that's why 1 cubic centimeter weighs 1 gram. Anyways, this table is talking about 10 cc's of the substance, 10 cubic centimeters.
So that's how much heat is necessary to raise the temperature of those.
So to get water from -25 degrees C to 0, it takes 522 joules of heat. To get it from here to here, it takes 522 joules of heat. So which phase change? First off, what are the phase changes? What do we specifically call them? They all have words. You used one of them for 2 minutes ago, Anna. Ice is not a phase change.
Vapor? Vaporization?
Vaporization, yeah, we call it something
Steam.
different.
Oh.
No, but
Evaporation?
What?
Evaporation?
Evaporation, sublimation, and there's a C word.
Concentration.
oh yeah.
This is a backwards one. Think backwards. If
Condensation.
Oh, yeah.
Condensation.
condensation.
I know
Okay.
that.
So
I don't know the word.
you don't know. Okay.
Condensation is when water condenses. It becomes a liquid after.
Did we cover them? I think you missed one, by the way.
Yeah, we missed a couple.
Yeah.
We missed 2. We missed the easy ones.
Yeah, we did.
Melting and freezing.
Oh,
No
yeah.
special words for those.
Melting, freezing.
Well,
And
fusion.
then boiling
Or-
isn't
yeah.
one of them.
Are there 6 words about that?
Yeah.
Well, yeah, because back and forth for 3 phases. Yeah. Well, there's more. I mean, AJ mentioned sublimation, which is where something just skips a solid or skips being liquid completely. The opposite of that is deposition, when you go from being a gas to being a solid, skipping the liquid phase.
Deposing.
Deposition. Depositing. Yeah.
I was trying to be.
Oh,
consistent.
deposition. Okay.
Are you sure it's depositing and not deposing?
I'm sure it's depositing, yes.
Okay. So melting is turning from Vic.
solid to liquid.
What?
Solid to liquid.
Good. Mick.
Liquid to solid.
Okay.
As we do this.
If you don't know, it's okay.
Liquid to gas.
Good. You don't know, it's okay. You don't know, AJ?
Solid gas.
Correct. Solid to gas.
So it's like skipping from here.
And that's like
We'll
with
talk
liquid
about that.
hydrogen,
Yeah.
right?
We'll talk about that.
Yeah.
No,
Yeah, like
dry
dry
ice.
ice. Yeah.
Gas is solid.
What?
Gas is solid.
Good. This is the opposite of
Wait.
condensation.
No, that's to liquid.
That's to liquid.
Sorry. Thank you. I knew what I was about to say. This is the opposite of evaporation. And depositing then is the opposite of sublimating. These work together, these work together, these work together.
So let's talk about energy gain or loss in these. If something's
Right.
going from a solid to liquid, is it gaining or losing heat?
And hold on one sec. We're gonna. Okay. Yeah, go ahead.
All right. So
And then
gaining
we'll
or
talk
losing? Mick, gaining or losing heat?
Gain.
Gaining. Anna,
Losing.
evaporating. AJ,
Gain.
gaining. Sue, sublimating.
Gain or lose heat to sublimate, Sue. More heat, less heat.
Does it take more heat to be this?
More.
Yes.
Not small.
Condensation? Mick, what do you think?
Um,
Gas to liquid.
Lose.
Lose.
Yeah, who's doing a minus?
Lose heat.
All right. And
Depositing. Deposition.
Those.
Lose heat, because you're going backwards. Now,
And this should make perfect sense because anytime we're going from gas to something else, it's lower because gas has the most energy. And it should have the most internal energy because, well, that's why it's gas. The molecules moving around so much that they're not bound by gravity as much. They're not stuck in the form of a liquid. They're not constrained together in the form of a solid. They have the most energy to move about.
what do you think we want to say about the starred items?
It's
Right.
unusual.
I concur. I think that's a good word. Unusual. Is it, I want to know, is it possible for all substances? Or do you not know? Is this possible for all substances? Can water sublimate? Can water deposit?
I think you can sublimate.
Yeah,
Okay, give
you just have to have.
give an
a really
example.
low-
You stick clothes out, wet clothes out in the winter, and the water doesn't the ice sublimate.
They freeze dry, so to speak.
Yeah.
Yeah. Another example would be, if I may, in the Arctic regions, water still gets in the atmosphere somehow. Sun heats the snow. The snow doesn't melt, but it sublimates. It becomes water vapor right off the bat.
Is it possible for all substances? We're going to say yes.
Under
However,
circumstances.
That's extreme.
Yeah.
extreme conditions. And so for
Yeah, I'd say more like specific conditions, but than extreme because it happens all over the world.
yeah, but I'm saying for all substances.
Okay.
So like in order for us to freeze mercury, I would say it's going to take relatively extreme circumstances. Why? Because it's going to have to. You're going to need to do what? You're going to need to extract a crap ton of heat. Does that make sense? Because here, at room temperature, it's a liquid. Okay? So in order for us to get mercury to be a solid, we're going to have to extract a lot of heat. And in order to get mercury to be a gas, we're probably going to have to add a lot of heat. In order for us to get hydrogen as a solid, we're going to have to extract so much heat. And so sublimation just takes this to the nth degree. It's saying not only are we having to get something from a solid to a gas, but we're going to do it and skip the liquid thing. So that basically means that it's happening over a shorter period of time, which means that that heat is all happening at once. So it's not like water often goes through sublimation. Mr. Gottschalk was talking about the Arctic, you know, that the water still does evaporate, and there's very little liquid in the Arctic, especially when you get all the way to the North Pole, especially in the dead of winter. Does that make sense? But water's still evaporating, you know. Set aside, if we ignore sublimation and deposition, which phase change takes the most heat? Which phase change requires the most energy?
Solid to gas.
No. If we ignore sublimation, we're ignoring sublimation. This obviously takes the most. These two take the most energy. Now, for a given substance, these are equal but opposite, right? Make sense? This is going to take the most because it's changing from two phases.
And the term you probably use in chemistry is endothermic and exothermic, right?
Yeah.
Giving off heat or absorbing heat. Endothermic are the ones that need heat. Exothermic would be they're going to a lower phase or lower energy phase, so they're giving off that energy. They're giving off heat. Go on, sorry. Just want to throw that out there.
I know, I was going to put them on here. If you want to write that.
Sure.
No, my question is, so now you basically have two choices. I'm asking you which phase change requires the most energy. From a solid to a liquid, or from a liquid to a gas. Which requires more energy? How do you know?
You use more heat.
You use more heat, he says. Are you sure?
You're getting something that has a set volume. Do you have, like...
I want concrete 110% proof.
Look at the graph.
Thank you. Look at the graph. AJ, go on.
From the ice to the water one is
yeah.
what, like 0.5 to 2.2?
That's the
There's a
point.
break in there, yeah.
Look at this. That's my point with the break. In actuality, this graph looks more like this.
That's why it takes so long for water to boil.
Do you see? There's only a difference of 4.3 here, and there's a difference of 5 here, and there's a difference of 22 here. You follow what I'm saying? It takes so much more energy, and you are right, Vic, but I just wanted a little bit more concrete proof given the information that we have. So much more energy for every substance to go from a liquid to a gas than it does to go from a solid to a liquid.
There's a very easy experiment you can do at home to prove this. Take a styrofoam cup or a paper cup, fill it with water, stick it in the freezer, let it freeze. Okay? Then take another cup of water, just at room temperature, and put each one in a pot. Okay? Put the frozen one in a pot, put the room temperature one in a pot, turn the stove on, and see what happens first. Does the ice melt completely first, or does the liquid boil completely first?
Does that make sense?
I would bet you that the ice would melt.
Guaranteed. You guys know as well as we do. Because
we're talking about, okay, not bringing it to a boil, but actually having it all boil off. Okay?
I mean, you can melt ice with the energy in the room. You know?
It's possible that the water will start boiling before the ice is completely melted, but the ice will completely melt before the water finishes boiling, right? Before the water, I mean, how long, have you ever put a pot of water on the stove and had it boil completely off so there's no liquid left? Probably not. It would take a long
Does
time.
water...
Like stock, like chicken stock.
Forget about it.
What's...
Okay, yeah.
Here's the question. What's the definition of boil? I actually don't know it off the top of my head, to be honest, because a lot of the time you would say, well, here's the case, is that water boils at 100 degrees. So my question for you is, when it rains, it's not 212 degrees outside, and the sidewalk gets dry. Do you follow me?
This is a good discussion. I like this.
You know? Okay, so I asked what the definition of boil was, because my head is turning, cranking, and I'm not that smart, so I propose a question to you, that this table says it takes 100 degrees C to boil water, right? To change from liquid to gas. So now my head's cranking, and I'm thinking, okay, it rains outside. Sidewalks, streets, everything wet. And then sun comes out, 2 hours later, hour later, everything is dry. But it was not 100 degrees C outside. If it were, we'd be very hot. We would die. Agreed?
Yeah, that's nothing to do with boiling.
The definition of boiling has more to do with what it looks like than what's happening.
Phase change. I mean, that's what we're working
If you
on.
put a pot outside to gather rainwater, it won't disappear after 1 hour to an hour after the sun comes out.
If it's just a thin coating of, I mean, if it's just wet and not standing water, it might.
I'm confused.
Out.
Yes, Anna.
Okay, so is boiling between C and D or D and E? Or is it between both?
Boiling is at D.
Boiling is at D. The letters are the lines. Boiling is at D. Because look at this.
Because if it skips D, then it could.
Hold on though. The question that I proposed before was: are heat and temperature directly proportional? They are. When we're not going through a phase change. This slope, this slope, this slope are all the same. If you look at your graph.
Yeah.
And that's the thing. You're not boiling, but you're also not skipping D. How is that possible?
So, well, we're now talking about two different things.
I do want to get back to what boiling is in a second.
I agree. Just to clear it up, so this helps, because I would further want you to understand what my conundrum here. What is A? What's the substance of A and what's it doing?
Ice.
It's ice and it is heating up.
Yeah.
It's heating up. We would call it. It's not melting, Mick. It's heating up. There's 30 degree below zero ice and there's 10 degree below zero ice. They're both ice. They're both cold. One's colder.
Yeah.
So we have ice heating up. What about B now, Mick? Here's your word. Go ahead.
No.
Melting. Beautiful. Is it actually melting? Well, yes. This is taking the energy. And it's what temperature are we at B, Mick? You don't need Mick.
Yeah.
You know about ice?
Sure.
When ice melts, it's at zero. So is there such thing as 0 degree water?
Yeah.
Very instantly.
Ice cold, yeah.
Right here, very instantly. 0 degree water. Just for a little bit.
Or it's where it's all 0 degree water, you mean?
Yes.
Okay. Because I mean, during this phase, you'll have part liquid
Water.
0 degrees, part solid 0 degrees.
Yeah.
Typically, if you time it correctly with a water bottle, you put it in the freezer, and right before it actually freezes itself, you can grab it, take it, and shake, and it'll turn into ice. It's called, what is that called?
Supercooling.
Supercooler. So if it's like 1 degree or 0 degree water, it hasn't quite gone through this phase of B, you shake it,
That's actually
it's gonna
different.
turn to
It's
ice.
actually below 0 degrees, but it hasn't frozen.
that doesn't make sense.
Why not?
Why would it be below 0 degrees if it hasn't frozen?
Because it needs a freezing nuclei. It
Oh,
water
right,
needs something
okay,
crystalline.
got it. C, what are we doing?
Water.
We're water and we are,
Yeah.
we're heating. Good.
Heating liquid water, yeah.
Yep, heating liquid water. D, Sue? What are we? What are we? Boiling what? Ice?
Water.
Gas? Yes, boiling water. This is still in the water state, and it's in the water state for a long time. Boiling.
So nothing has evaporated.
It's in the process. This is where the
There is
particles,
stuff evaporating.
the particles are going from close together to further apart. So as time goes on, little parts of, yes, your liquid are evaporating in this phase.
And we call it the heat of what? Heat of fusion was when we're switching from solid to liquid or vice versa. Or switching from liquid to gas. It's not called heat of evaporation. It's a different word for it. It starts with a V.
What is it? What is it turning into? It's water
What do we
blank.
call water in
What?
its gaseous form? Yeah.
Good. Heat of
Vaporization.
vaporization. Those are terms you need to know. Heat of fusion. What is it?
Turning from solid.
What? Yeah, energy. There you go. Energy.
Energy used to change.
And you could just say between solid and liquid. Okay?
Solid to
It
liquid.
can go both ways, because you can go liquid to solid and you need to release that heat of fusion.
I'm going to put
Yeah.
arrows on both ends.
I like that. That's a good idea.
Okay? You guys capiche?
Yeah.
Okay? And then heat of vaporization.
I'll bring some ice in tomorrow if I remember.
Energy used to change liquid to gas back and forth. It's either energy used or energy lost. Can you read that soon? Sorry. Vic, you good? You don't take notes, it's all good.
Vic remembers everything. Alright, so that's D. What's happening in E then? What's happening in E in the graph?
That's just vapor then.
Vapor doing what?
Yes.
Moving around.
No vapor.
Once it's vapor,
Oh, heat
is
it up.
allowed to increase temperature again, yeah.
What's that one?
Question.
Heat of what after?
Heat of vaporization, heat of fusion.
You both wrote it messily, yeah.
Yeah, we did.
Used to what?
Okay,
Used to change liquid to gas.
let's talk about
the
boiling.
Used to change
Solid to liquid. But that's a double arrow because it can either change solid to liquid or change liquid to solid.
These are both used in both endothermic and
Yeah.
exothermic reactions. Alright, so boiling. The reason it's called boiling is because the water looks like boils. As the surface of the water, you have these bubbles growing, right? That's why it's called boiling. So what does that happen? What do we see when we see the bubbles on the surface of a pot of boiling water? What does that represent? AJ, you look awestruck. You did, and then you're gone. So either you're awestruck or completely bored. Or maybe you know what's going on here.
I was actually thinking, when you said boiling, I was thinking, what's the boiling point for skin?
You guys know what a boil is? Boils are
You could try
disgusting.
to
They're like when
boils.
your skin,
Yeah.
we don't have much more anymore, but it's like when your skin becomes
One
one
of
of
the 10 plagues,
Excuse
yeah.
me.
you know, it's one of the 10 plagues, Vic. No? A boil?
So I was thinking.
Like if you had
Like
It's
you
a
have
bubble.
chickenpox or something.
it's a big bubble on your skin.
They're nasty,
Yeah.
pus-filled sores.
Like
Ew.
Full of
bliss.
white
Yeah.
pus. Yeah.
So, are they
You have
nasty, pus-filled bubbles in the pot of water?
Zits are technically small boils.
Ew.
Yeah, so.
Alright, so what's going on here? What are the boils that we see on the surface? What are those things?
Air.
Air.
Air! What the heck? There was water in here. Where the heck is the air coming from?
It's heating the bottom more, so there's more evaporation.
Beautiful.
But what's
Yes.
but what else is there more of down here? And here's when we go back to last chapter.
There's more
This
heat.
is the cool part. And more pressure,
I see.
right? We have air plus water down here. You got that dark one, please. Thank you.
Does that make sense? The temperature is the most down here because that's where the heat source is. The same time you have more pressure. So that thing, heat wants to, or heat rises, temperature, things that are less dense want to rise. Since these are hotter, they want to rise.
And so this bubble, as it goes up, as it rises, it is under less and less pressure. Therefore, it's not constrained as much, right? You get a little bigger.
Does that make sense?
A little bigger.
There's less pressure and
A
so
little bigger.
And
Finally, it bursts on the surface. Yeah. So that's what's
Good.
happening. And you can see the same type of thing if you look. If you pour a glass of soda
yeah.
out of a can or a 2-liter or something, a clear glass, you will see the smallest bubbles on the bottom and the biggest bubbles toward the top.
So that's boiling. Now my question again is this table true all the time? How in the world does water, when it rains,
Yeah.
it's not 212 degrees Fahrenheit outside, it's not 100 degrees C outside, you and I all agree to that. How does that work?
And it's not boiling either.
The change of the temperature on it is.
But this table says it requires 100 degrees.
Well, that's
Yeah,
not
but
true because
that-
in high altitude it's lower.
But we're in regular sea level altitude right now.
The red water is like it doesn't disappear.
It didn't disappear.
It just turns into this really small.
Runs off into the grass.
Here, I'll give you a clue. This has something to do with it. I don't know how you work this.
Press the trigger and aim it.
Got your,
He's killing you.
Anna's surface skin temperature is 90 degrees. Open your mouth.
Open wide.
Open wider. Anna's mouth is 93 degrees.
That's so weird.
Why?
You're hot.
If we could get Anna's insides even more, they would be
Hotter.
98 degrees. Just because the air outside is 80 doesn't mean the surface. What's that? It does not, the surface of this does not get to 100 degrees. We'll talk about it a little bit more. We'll
Yeah,
finish
but
that
when it's
discussion.
evaporating and you touch it when it's in the process, it's not hot to the touch. I mean,
Right.
this happens on a 40-degree day.
Yeah. We'll talk
I mean,
more.
you see the
It has to do with
icing.
yes, it has to do with the directness of the sunlight, amongst other things. Because,
Is it
correct
like
me
a
if I'm
magnifying
wrong,
glass thing?
this
Because with a magnifying
is the
glass,
same.
it forms-
This isn't necessary.
Right, yeah, I would agree with that. It doesn't have to.
See, more than that, I don't, that's what I was trying to do. I was legitimately hoping that we could crank it out. Because I don't think that that's the case all the time.
I don't either.
But it has to be, because in order for it to be a vapor, it has to be above 100 degrees.
How hard is it?
Yeah.
The temperature is molecular water, you know?
That's true. And that's what Sue was getting at, is that you're
They're all
thin,
they're all
and they're all spread out.
Table second.
How does that
That
make
is
work?
so cool.
Yeah.
Mr. E,
Wait, I want to see
So-
you
are we
first.
gonna have more time to work on this?
No, do at the very beginning of class. I told you
You're
that.
84.5. I don't know, it's so cool.
This is essentially, the laser is just an aim. Okay? It's an infrared sensor. It deals with infrared light, heat waves. I'm going to try to come out to tell you the temperature.
I love the coast. It's so cool. So I got a house.
How much was that thing? 50 bucks?
That's, no.
Money.
Newwave.com. It's a great site for technology, computer type
I
stuff.
think I kind of want to buy one.
This is just this is like the cross section. Down here, let's see, there are different scales. This is meters. If you're 2 meters away from whatever you're trying to get at, then it will aim, it's giving you the temperature within a quarter of a meter of area, 0.25 meters area. Okay? In other words, if I measure you from here, I'm looking at your whole head, not just your mouth, even though I'm looking at your mouth. So I'm at 90 degrees. If I want to get accurate for your mouth, open up, I go closer.
That's 3.5.
94.
That is so cool.
So you get the pass. You get the pass.
You hear what he said.
You get the pass.
Go.
Waiting for the pass.
For what?
61. That doesn't go all the gold within the locker.
Yeah, it wasn't sure. Get the pass.
Who's got it?
I want to have one of those.
Well, it's been a couple hours.
It tells you the temperature, so you
Mr. G.
Yes, Sue.
A
pass? You always want to pass, Sue.
Yeah.
You could ask those questions, we get out on time. I've seen mistakes on Snapple caps before. I told you about the Arctic thing, right?
Yeah. So that's why I said we gotta Google this to see if it's true.
Here you go, Sue. You're welcome.
I love that.